Since the mid-2000s, we've been having a lot of sparsity promoting numerical techniques, and this includes lasso or L1 regularization, where you basically take your loss function and you regularize it not by, say, the square of the norm of the weights, which will give you ridge regression, but instead what we do is we regularize by the sum of the absolute value of the weights, which is an L1 regularization. And a particular algorithm for implementing this is called lasso. What ultimately ends up happening is that a very few of your weights are going to end up surviving this L1 regularization technique. And so since only a few weights end up surviving, you only need a few basis functions, and you can do this with much fewer samples coming from, say, a CT scanner. But this leads us to the next thing, and that is the SINDy algorithm. So the SINDy algorithm does exactly the same sort of thing for a dynamical system. Essentially, you might have an unknown dynamical system, and I said last time, maybe you know it's within the span of this collection of basis functions. But maybe this span of basis functions is much, much larger than it needs to be. And what we want to do is we want to use an L1 regularization technique, or lasso, in order to pare down the number of non-zero weights out of this huge collection of basis functions. And so this will come in handy if we take a look at something like the Duffing oscillator or the Lorentz system. Now we know that these correspond to polynomial dynamics, but maybe we don't know exactly what a fixed degree should be. So we might say that we want to have like a 50-degree polynomial in order to approximate, these dynamical systems, but we only need like 3 basis functions in order to really figure out what those should be. And so that leads us to trying to look for some sort of sparsity promoting techniques. So why don't we go ahead and talk about the SINDy algorithm. All right, so let's talk about the SINDy algorithm. So the whole idea here is that we're starting out with a collection of snapshots that describe a trajectory. This trajectory corresponds to a dynamical system, so x dot is equal to f of x, and we'd like to figure out what f is because f is generally going to be unknown. So what we do is we select a collection of basis functions that we're going to use to represent our dynamics. Now, we don't know what the dynamics are, and so we actually don't really even know what a good selection of basis functions will be. So we pick something sort of generic, something that we know can approximate pretty much any function. And so this could be, a collection of monomials or polynomials or, sines, cosines, things like that. Something that we know will sort of make a complete set in some sort of approximation space. But we need to figure out what the weights are going to have to be. Now, the complication here is that we don't actually have any direct observations of our dynamics. We only have the trajectory of our system, but the dynamics are actually correspond to the derivative along this trajectory. So the method that Kutz and Brunton use elects to take numerical differentiation in order to figure out some samples of our dynamics. So now let's go ahead and see how we can use this notion in order to figure out what the weights have to be for our approximation. If you take a look at our trajectory and you start taking numerical derivatives there. For each time step, we can take a numerical derivative, and then we can go ahead and make a stack of the numerical estimations of our derivatives along our trajectory for each snapshot. Now, on the other side, this should correspond to f evaluated at our snapshot, but to the best of our knowledge, this is going to be the linear combination of our basis functions. So we have, say, w1, w2, w3, all attached to y1 at our state, y2 at our state, y3 at our state, etc. And so we turn this into a row of our basis functions evaluated at our state, and then we multiply it by the column of our weights. And we do this for each snapshot of our trajectory. Now, we would like to resolve this linear system, and we'd also like to resolve this linear system where we don't have to use that tremendous number of weights. The best way to go about this is to use an L1 regularization. The L1 regularization is going to find the smallest number of non-zero weights that should satisfy this linear system. Using this L1 regularization does give us a reduced order representation of our dynamics, where we only select a reduced set of the basis functions that we started with, and it usually is going to be a very small subset of those basis functions. But the method of Kutz and Brunton does have a few drawbacks, and the biggest drawback is going to come down to the numerical derivatives. You have to select a method of numerical differentiation that is going to give you a very robust numerical derivative, and any of these methods end up being very sensitive to any sort of signal noise. So differentiation on a signal noise system could give you anything from, say, negative infinity to infinity. I mean, white noise has extremely steep curves, even if it is going to be very, very small. And so numerical differentiation is hit by that very easily. You could try doing things like moving averages, but still that only pares it down to a certain amount. And Kutz and Brunton, I think they actually appeal to doing things with a total variation norm. After a certain point, that's still not going to work very well. So what I would like to do is I would like to tell you how we can use the inner product space that we just talked about, and we can simultaneously solve this inner product problem, and we can also resolve this noise issue that you have coming out of here. And this is ultimately comes down to what we'll call a weak formulation of the SINDy algorithm. So what do I mean by the weak version? It doesn't mean that my algorithm is actually going to give weaker results. Now, when you say something is weak in, say, functional analysis, you're trying to resolve the problem against, say, an inner product or a functional of your system. So the weak formulation that we're going to be looking at here comes through function composition, and we know that function composition can be represented as inner products in a reproduced kernel Hilbert space. So what we do is we start with some function g inside a reproduced kernel Hilbert space, and what we're going to do is we're going to take a look at our dynamics. So we're going to take g, we're going to compose it with our dynamics, and we're going to take the time derivative. What this ultimately gives me is the gradient of g composed with my dynamics times the time derivative of my dynamical system, which we know is actually f of my dynamical system, where f is what we're trying to figure out. We're going to be looking at f as a linear combination of basis functions, and so we can go ahead and expand this out. And so what we end up getting is the gradient of g composed with our dynamics times this linear combination of basis functions all evaluated at our dynamics. Now what's really interesting here is that if I take this quantity and I integrate it from 0 to t, what we end up getting is that on one hand we're going to have g evaluated at either endpoint of my trajectory, and we're going to take that difference. This is a fundamental theorem of calculus. And on the right hand side, we're going to be taking a look at the integrals from 0 to t of the gradient of this known and selected function g, evaluated at our trajectory times each one of our basis functions, and and that sum according to these weights. And so what I can do then is that for this particular observable or function in my Hilbert space, on one side I can make this linear equation, and I can put that quantity of the difference at the endpoints in my first row of this vector, and this should be equal to all these integrals against our basis functions and using our observable, or the gradient of our observable, and then this row times a column of my weights. And then I select different observables and possibly even different trajectories, and then I can make a huge stack taking the difference at endpoints according to these observables and these trajectories, and then I can make all of these rows of our basis functions where you take these integrals along these different trajectories and multiplying by the gradient of our various observables. And so then this gives me a linear system that we can try to solve in order to find these weights. Now, why is this better? One thing that makes this better is that doing numerical integration is going to be way more robust to noise than, say, numerical differentiation. And in a lot of our tests, we have found that the weights that we find for these basis functions using something just like matrix inversion ends up being very, very, very accurate in the case of, say, the Lorentz system, where we actually know the solution. And we did experiments with something called the EMPS dataset from nonlinearbenchmark.org, and we got fantastic results there. And that's not even using the L1 regularization yet. But if we want to get a reduced order model, say we used a tremendous number of basis functions, and so for those other ones we used, say, 30 basis functions when we only needed 6, but you can take that higher if you want. So we use like third degree polynomials and second degree polynomials, things like that. But if you say use a fifth degree polynomial, you're gonna have a huge number of basis functions. And so if you want to use that collection of basis functions, you'll probably want to use a reduced order modeling technique. And that would come from doing L1 regularization and trying to resolve this matrix equation. And we did that, and what we found is that while the weights weren't completely accurate, we did find that the weights that should be non-zero were a subset of the reduced order model that we started with. And so what we can do then is we can just go ahead and use an L1 regularization to give sort of an indication of what basis functions we really should use, and then just eliminate all the other basis functions, and then just go ahead and run our regular matrix inversion technique in order to find the weights. Now, the question is, what are good observables to use? So we talked about last time that if we select a collection of basis functions, these are going to represent features for a kernel function for a reproduced kernel Hilbert space, and then resolving this parameter identification problem is actually going to end up giving you the projection of a dynamical system that gives rise to a densely defined Liouville operator over this kernel space onto a collection of basis functions that we represent through Liouville operators, and this gives us this particular inner product. Now we're free to choose these test functions to be anything we want. It could be any sort of C-infinity function or maybe finitely differentiable function. And so what we used in a lot of our experiments was we actually just used Gaussian RBFs, which are pretty typical test functions in physics and other places. Then if you use these RBF functions, you can just choose their centers to be close to your trajectory and you'll actually get a fairly well-conditioned system. Now, one thing that this L1 regularization can do for us is it can actually help take care of that indeterminacy that we talked about in the last lecture. Now remember, since we only have dynamics sampled along a single trajectory, we can add any sort of function that would be 0 along that dynamics and get a perfectly valid representation for what the potential dynamical system should be. One thing that this L1 regularization does is it asks for the simplest explanation for our data. In a sense, since there is no real way of determining if there should be another function added to our dynamics, to generalize it to the rest of Rn, because we've only observed it through this little keyhole of our trajectory, what we can do then is we can just say, all right, we know that there might be other functions that should be added to our dynamics that might be 0 along our trajectory, but we're going to try to pare it down as much as possible using this L1 regularization. And so that is another function of this sort of reduced order modeling. I don't know if Kutz and Brunton talk about that at all in their work, or if they've even thought about it. Maybe they have. I mean, people think of a lot of things they never really write down. I found it a very slick way of handling this problem that was handled automatically by them selecting to try for an L1 regularization. So I thought that was pretty cool. Anyways, so that's the SINDy algorithm. So why don't we go ahead and end this lecture by taking a look at a few examples in MATLAB. Okay, so why don't we go ahead and take a look at some MATLAB code. Now the code gets pretty involved in here. Ironically, it's the easiest theoretically to describe in terms of parameter identification and approximation for system identification, but coding it up actually ended up being a little tricky. The tricky bits get to be generating the basis and then generating also your test functions. And so this doesn't all kind of cohesively come together like most kernel function methods, which all surround, say, the gram matrix. And so had to do a little bit of hacking in here. I have a whole bunch of clever tricks that I'll make whole videos on describing. In particular, when I make the monomial basis, I pull some ideas from number theory in order to keep track of exactly what the highest degree of the monomial is. So, yeah. Anyway, so it works super efficient, it's super fast, and it works really, really well. And so I'll walk you through here, I'll give you a tour of the code, and after I give you a tour, I'll just run a couple of examples. I have two examples I'm going to show you. One is going to be with Lorentz data, or with the Lorentz system, which is a chaotic system. It's one of those really cool butterfly-looking systems that you see on people's t-shirts when they talk about nonlinear systems theory. And then I'm going to show you the Duffing oscillator. The Duffing oscillator is a nice two-dimensional system, and I can show you exactly how good of an approximation we got. And you're going to see it's an excellent approximation, and unlike the regression problem, the occupation regression system identification method I showed you before, this approximation will span more than just the local area. But if you get just the right basis set, I mean, that's the entire function itself. Now, of course, there are the issues that come up with having possibly functions that are 0 along our trajectory, but you'll see in here we get exactly the right coefficients. And this, I'm not even using a lasso method or L1 regularization yet, and you can add that on here with like almost no change. For here I'm just using a pseudo inverse, and yeah, it's working fantastic. So why don't we go ahead and take a look at the code. All right, so in here, this is the version I did with the Gaussian. I also have another one that I did with the exponential dot product kernel. The code is more or less the same. There's just like one little trick that you have to use in the middle of the integration, but don't worry about that. So the data sets that we're going to be using, so if you take a look at the Lorentz data set, so this is what we have here, and so if I say plot 3, and let's see, I already did this before. So boom, this is the Lorentz system. So this is a sort of chaotic system, pretty really pretty looking. It stays roughly in the same area. It is contained, but the idea is that it is chaotic. So you can't. So if you start with 2 points that are close together, before long they're going to be very, very far apart. And so that's the Lorentz data. And as far as the Duffing oscillator goes, I mean, we've seen this already. So we can say plot W1 here and W2 here, and boop, and there we go. So this is the Duffing oscillator example. So you'll remember the Duffing oscillator was a two-dimensional system that we augmented in order to make it a one-dimensional system. And so one dimension of the Duffing oscillator should just be x, and there shouldn't be anything really tricky there. And then the other one should be x minus x cubed, which was the whole system is supposed to be like x double dot is equal to x minus x cubed. And so we should really just see a 1 on the basis function that is a monomial that corresponds to just x, and we should see another one for the second dimension that corresponds to the x, and then we should see a -1, and that's going to be the whole deal. And so here I'm going to run with the second data set, and then later I'll show you the Lorentz trajectory. And yeah, I'll write down the Lorentz system equation here. I forget exactly what the parameters are, but they're going to match almost exactly here. And I might say that and forget to do it, but yeah, whatever. So let's go ahead and take a look. So in here, this is where I collect my data. So this is the Duffing oscillator data just generated with RK4. I forgot to put H in there, so I define it here. And then if we go through here, so I want to use Simpson's rule. So Simpson's rule usually requires an odd number of points, so I just chop off the last in time. That's not really a big deal, especially when you have like 1,000 points. Losing one isn't gonna hurt you too bad. And so then this is my Simpson's rule vector, just like last time. So it goes 1, 4, 2, 4, 2, 4, 1, something like that. And then this is the Simpson's rule matrix. We don't actually need this here. It was a remnant from another thing I did. So here, let me just delete that now. All right, so get the dimension from the data set. So basically it's going to be, the data set is going to be listed as a column for each time step. So if it's a two-dimensional system, then each column has 2 rows, and each column represents the next time step in the sequence. How many polynomials do we need? So what degree of polynomial do we want? So we want all of the monomials of dimension, whatever this is, dimension n, and I want these monomials to have a degree of at most 3. So I can have x1 cubed, I can have x1 squared, x2, I can have an x2 squared, things like this, right? So this is all the prime stuff that I did. Essentially the way you start out is you just start with a polynomial, just a vector of polynomial. So you just take, like, say, some singleton, and we raise it entry-wise to 0 to the polynomial degree. So you get like 1x, x squared, x cubed. Then if you want to go to the next dimension, then you basically take that guy and you're going to do some sort of tricky multiplication. I think it's going to be take that column, you multiply it by a row of the second variable evaluated at the same rate, so the same exponents, and then that'll give you matrix, and then you reshape that into a column, and then you just do that again and again until you have all of your monomials. But then you'll have some that exceed the actual degree that you want, and so then you go through and you use this number theory trick in order to trim it down. That's what all this is. So then eventually what you get is you get a monomial basis ND, and so I basically have my monomial basis that we made through all this funny matrix multiplication, and then I make n copies of it that I put in here. So I have a copy for each dimension that I'm going to be working with. And so then I count the basis size, and then I evaluate each one of these basis functions along my trajectory. I'm going to need that later when we perform the integrations. And so I do this all separately here, so then I can just call to these. I'm assuming I have enough memory in order to do this. But I don't want to keep regenerating that and reevaluating that every single time we're building our matrix, because then that's going to bog the system down really quickly. So now I need to make some test functions. I'm just using, here is a Gaussian RBF. And so I'm selecting my centers, and I'm just choosing them to be more than the basis size, just 3 times the basis size. There's no real reason why it needs to be that. It could be exactly basis size, but I'm just trying to sort of cover all my bases. In any case, so I just choose some massive number of centers, and then I'm going to use a Halton sequence, and so that basically makes an n-dimensional collection of points inside, say, an n cube. And so then I need to resize that n cube to match our workspace, and so then I get the maximum along each dimension and the minimum along each dimension of my trajectory. And then I just go ahead and I rescale those Halton sequence, and I make it so that each one of my centers is a column in a matrix, and then so then all the columns together are each one of my centers. Right, and so those are going to be the centers that represent my test functions, which are Gaussians centered at those points. Okay, so now we need to make the big matrix, and so we're going to run through all of our test functions. Those correspond to our centers, and this should actually be total centers, comma, basis size. It wasn't causing me problems before because my basis size was bigger than that. Let me just make sure I put the right. Yep, there we go. All right, so there we go. And so then through here, this is just me making the matrix. It's a couple of tricks using the Gaussian. Remember, we're going to be taking the gradient of the Gaussian, and so then the gradient of the Gaussian is, so if the gradient of the Gaussian at x minus y, it's going to basically be minus, so it's going to be minus 2 over mu times x minus y times the Gaussian RBF itself, and that's what I do. So here I'm just basically taking x minus our centers, and so that's x minus y, and I multiply it times this. This is just our Gaussian evaluated along the trajectory. I put it up here outside of this J loop, so we don't have to keep making it over and over again. And so then this just gets pointwise multiplied by those basis functions evaluated along our trajectory. No big deal. And so then I multiply this times this. Technically it gives me a matrix, so I just take the diagonal of that and multiply it by whatever coefficients I need to. H over 3 comes from the Simpson's rule vector. This comes from just the inside of the Gaussian, and this is where I put those difference of vectors. And so then here's my Simpson's rule vector. So putting this all together just basically does an entire integration in one line. All right, so then I take that and just run this loop, and so that makes me that giant matrix with our test functions and our basis. All right, now you need to evaluate the other side to invert against, and so basically you just have this, what I call an evaluation matrix, and then so you just, for each one of the centers, you evaluate that test function at the endpoint and then at the beginning, and then you make that vector, and then ta-da, you just get the weights by doing a pseudo inverse here of our big matrix against the evaluation matrix, and then you can use those weights against our basis functions in order to get our approximation. So let's see what we get. So boom. So which data to? Oh no, I broke something. Oh yeah. Okay. Shoop. You probably noticed me doing that earlier. All right, now let's try it again. Here we go. It ran. Okay, cool. So it ran in 2 seconds, and this was for a polynomial of up to degree 3. And so this should match what our Duffing oscillator is, and that's what this data is corresponding to. So let's take a look at weights, and you'll see we should have a 1, a negative 1, and another 1. So here's 1, here's another 1, and here's a negative 1, and everything else is a flat 0. It's amazing. So why don't we go ahead and see exactly how good of an evaluation it did. So this is a quick bit of code just to get a few plots, pretty pictures for the video. Our second dimension error is on the order of 10 to the minus 9, which is excellent. This is in this region where our trajectory lives. And so yeah, so that's really good. I mean, 10 to the minus 9, the shape doesn't really matter. I mean, like that's a great approximation. And so then again, 10 to the minus 9 error here for this shape does not matter. I mean, this is just your error plots. But shape does matter here. So this is our second dimension, and this is our first dimension. So remember, the first dimension is just x1, and so this is just should just be a linear equation and constant in one direction. And this should be x minus x cubed, and so that is pretty much exactly what this is, and constant in the other direction as well. Okay, so Duffing oscillator identified, and that was only took a few little seconds. And then if I come in here and I change everything to be the Lawrence dataset, same exact code, it runs, and it runs, and it runs, and boom, it gave us something. Let's see what our weights are. And yeah, so I mean, I didn't tell you exactly what the weight should be, but basically it should be around 10 and a 10, or minus 10 and a 10, and yeah, 28 and -1, etc. So these are pretty much exactly on point for what they should be. And you can improve these. You can make a bunch of adjustments to your kernel functions, the centers and things like that, in order to try to figure out, maybe like suss out a little bit better. Things that can help you get better results are maybe to use more points if you have them available to you. So smaller step sizes will give you better estimations for your integrals, and so that's good. And generally speaking, as far as your mu's go, they should correspond roughly to what you're seeing out of your data set. And so here I chose something as like, so for the Lawrence data set, the largest point that we go in any direction is about 20, and so I just chose this, so we divide by 20 and multiply by 3, so it doesn't have to be so strict. We don't want to put everything exactly into a ball of radius 1, but yeah, that's the idea. And so you just match mu with roughly on the scale of your problem. It's especially important when you talk about the exponential dot product kernel, because you can have the square of the size and thrown into the square of your largest vector thrown inside of an exponential, and that can get huge really fast. So you need to make sure you just damp that down a good deal. And so make sure it makes it so that your exponentials don't leave a region. Never evaluate a point that's maybe more than 5 or something like that. And I've found that generally this works out well. And I guess yeah, so that's the code, and yeah, it works really well. So this is the parameter identification code. I didn't institute the lasso L1 regularization just because it didn't really need to. If you wanted to do that sort of thing, that would be, I would worry about that more when you have something that's the polynomial of degree 10, and then you get a huge basis set. And so then lasso will help you pare down the number of basis functions that you really should be paying attention to, and then you can reduce that set and then check it again. But otherwise, the matrix computations and everything else like that are identical, and so it's just a matter of how you choose to resolve this system of equations right here. Okay, so with that, I think I'm going to stop, and thank you for watching.